Hi guys, first of all, in the recording, it's being recorded, so the slides will be shared as a PDF. So please look at the slides as well for those in the recording. Just going to get set up now. Okay. So in the recording, what can you see? Yep, you'll be able to see that. That's amazing. Okay, we'll get started. Hi, my name is Matthew. I'm one of the transport tutors for 2024, and I'm just going to go over the crash course for the CVEN3401, Sustainable Transport and Highway Engineering. Before we start, I'd just like to acknowledge the traditional custodians of the land that we gather on today, the medical people, and I'd like to pay my respects to the elders, both past and present, and extend that respect to other Aboriginal and Torres Strait Islanders who are here today. So my name is Matthew. I'm one of the transport tutors for T2 2024. Actually a student, if you don't believe me, I'm a student. So I'm a fourth year civil engineering and commerce. So all the third years, I'm 1 year ahead of you guys. And I'm planning to do a research thesis in transport engineering next year. So my year is a 5.5 year degree. I squished it to 5. So I plan to do a research thesis in transport engineering. Happy to discuss about that afterwards. And I'm also a student as well, and I'm doing wastewater as a student this term. So if you see me in one of the classes, just feel free to say hi. I'm not that intimidating. But yeah. So what is this course all about? This is the first introductory course in the discipline of transport engineering. Okay? So you may think to yourself, why transport? And I'll go over why later. But basically, in a nutshell, what you're going to do in CVEN3401 is week 1 to 5, you're going to get introduced to the concept of transport planning. And then week 7 to 10 is that you're going to design a road. Okay? So we're going to focus on road design as well as some road design for CVEN3401 for the civil engineers. For the environmental engineers in the recording, what you're going to focus on is you're going to focus on some analysis methods required for sustainable transport engineering. So I'm a civil engineer. I don't know about environmental engineering that much, but I would assume about emissions and all that. So Ellie, as well as Mihad, will go over how to do that. So you may be thinking to yourself, you've done many structural courses, okay? You've done many engineering mechanics courses, you've done structural analysis, you've done some steels, you've done some concrete, so you've learned about structures and you've learned about dirt and geotech as well. You've done soil mechanics, you've done applied geotech for engineers, okay? And you've done some water courses as well. But this is one transport course, right? So as a civil engineer, why do we need to study transport, okay? You may be wondering why you need to study transport, okay? There's 3 main reasons why we need to study transport as an engineer. 1, transport is so pivotal in the way communities function, and it really affects the quality of life. So as civil engineers, we design and build the built environment, and transport interweaves our community. So it gets from place A to place B, okay? Without efficient transport networks, it will lead to congestion, it will lead to hampered economic performance. Those are some simple examples. And the way engineers design and make decisions on transport will have an impact to the community and the way we live, whether it's social, environmental, and economic, and whether it's health. So you see above here, one more lane should fix it, okay? So sometimes we may make transport decisions such that we may want to extend the lane, but there's positive implications and negative implications. And one of the negative implications is additional traffic, because it's more desirable to drive when you have less traffic, and as a result, more people drive, that will induce demand, that will make demand, and that will reduce the desirability to drive. So those are some of the implications, more congestion. Another reason why is that an efficient, equitable, accessible transport network really provides opportunity to people. There's many examples to that. For example, you can connect. Public transport is really an essential service to connect to education, employment, healthcare, and social connections. Poor public transport hampers opportunity, especially for the most vulnerable. So there's a risk of, so if you can't drive because you don't have the money, right, to purchase a car or to get a license, there's a risk of increased social isolation and a reduced ability access services, education. That's particularly prevalent in Sydney, in western suburbs of Sydney, as well as in regional areas such as Coonamunra, Parks, wherever. So we really need good public transport networks for good communities. Three, transport plays a big role in emissions and environmental sustainability. So as more renewables go into the electricity grid, what's going to happen is that according to DCCEEW, which is the environmental agency focuses on climate change or whatever in Australia, it says that transport emissions are projected to be the largest source of emissions by 2030. So it's really important that we study transport so we can reduce emissions to mitigate climate change. So you see some of the decisions that we make. So instead of building a road, maybe we should cut down on highways and let's say build parks. So what are the implications on that? So that's some questions as transport planners we need to have a think about. How do we shift that demand to more sustainable forms instead of going from a car-centric city to more of a sustainable, active transport city with lots of mass public transport, for example. So that's what we need to consider as transport planners. So week 1 to week 5, as I said, is all about transport planning. So what you've looked at this week is you've done all your transport tutorials this week. We've looked at an introduction to transport systems and planning, and you've also looked at 4-step modelling. Next week will be on trip generation, trip distribution, so where the trip's going. Week 3, mode choice, so which mode should I choose? Traffic assignment, which route should I choose? Week 4, bit more on traffic assignment, applying the 4-step model holistically and looking at traffic flow theory, and week 5 is more on traffic flow theory. Week 7 to 10 for the civil students will be about a geometric design of rural highways and roads, which includes road design, route location process, and design practice of urban and rural road. Week 7, you'll get introduced to that topic. And you'll also learn a bit of kinematics. Week 8, you will look at horizontal alignment, so looking at curves on a road, so how to design curves based on the standard. Week 9 is vertical alignment, so you're looking at how to design against terrain, for example, hills. Week 10, you're going to look at cross sections and earthworks. These are the assessments for Tier 2 2024. You have 3 Moodle quizzes. What I heard, they're in person. Not in person, sorry. They're online, sorry. Apologies, it's online. Open book. So those are the 3 types of quizzes. That's what they're going to cover. That's what DB is going to cover. We also have a highway geometric design assessment. So your typical assignment, you're just given a set of questions and you just have to solve it. It'll cover all the content from week 7 to 10, and you have your final exam, which is based on 2023. It's in person, paper, and it's closed book, and you'll be provided a formula sheet. However, the formula sheet is only from week 7 to week 10 content, so we'll go through it later. So these are the 3 assessments. Some of the tips I have is that 3 Moodle quizzes, it's worth 10% each. I would highly suggest making condensed notes for each of the topics because it's open, if it's open. And you need to stay up to date with the workshop problems and do additional practice questions. So try to get practice questions from your older friends, okay? SevSoc is a great way to know other older people. So through SevSoc, maybe try to get some older person's question bank or whatever. You really need to practice if you need to get it for the HD. For highway geometric design, the main tip I have for you guys, please don't leave it to the last minute where you have to answer around 10 questions in week 10. So please stay up to date with the weekly content and do them sequentially as you progress through content from week 7 to week 10. So I'm not sure when that's due, but usually it's due at the end of week 10. So please don't grind out all 10 or 11 questions from that highway geometric design assignment to the last minute, because you will burn out and there will be a lot of late nights. Final exams. My tip is to, during the term, you have to keep up to date with content. Workshop questions, you have to do practice questions, and you need to review your performance throughout the term. So after the midterm quizzes, after the 3 quizzes, have a look and see where you went wrong, redo the questions, redo it again such that you're fluent. What I'm saying in my tutes, I say to my students, work smarter, not harder. So focus on the stuff that you are not good at instead of repeating questions that you already know what to do, okay? You need to focus on the stuff that you may not know, may not be the most confident on, and then from there, you'll be good. During StuBat, practice papers and practice questions, you really want to familiarise yourself with the formula sheet. So remember where the formulas are and how to apply them. So note that the formula sheet from 2023 only covers week 7 to 10, which is as follows. So you have all the formulas for circular curves, spiral curves, vertical curves, crest curves, sag curves, but they're only for the week 7 to 10, which is the road design component. The formulas you need to remember for the first half, right, for the final exam, you need to rote learn them. They're not in your formula sheet, okay? So let's just go over some of the weekly content. So what I'm going to do, we have I reckon we have around 30 minutes right now. So I'm just going to go over just a simple summary of the content. But for those who are watching on the recording, just a bit of a disclaimer, this is not a substitute to lectures. I have definitely omitted content in these slides to fit within an hour. So, and also because it's week 1, I don't want it to be week 1 info time. So this was based off 2023 content. It's not official lecture information. So Delia, the course coordinator, may add or omit information that's covered in this, covered here. So make sure you watch the lectures. That's really important because that's official information. What I'm saying is, from me as a tutor, as a person trying to help you, these are the stuff that I feel like is important. But I've definitely omitted stuff in here. Week 1. This week, you've looked at what makes up a transport network. So the different types of nodes, the different types of roads, okay? And you've also got introduced to the concept of transport demand, okay? So why do people transport? Why do people go from A to B? Because they have a reason to go from A to B, okay? They travel for a purpose. They don't just, for most trips, they don't just travel just for the sake of it, okay? Transport, so that's transport demand. And transport supply, the roads and all that, they must meet the needs determined by demand, okay? And you also have human factors and behaviours that's also influencing travel demand. In transport planning, there's many different types of models, but you have these 3 different types of models that they've looked at. You have microscopic models, which are more localized, right, towards more of a specific road section. You have a macroscopic model, which is more holistic. And you have a mesoscopic, which is a hybrid of both. It has both characteristics. Okay? And what you're also going to look at is you're also going to look at transport, this 4-step model for transport planning. So this is how to estimate the number of trips and to estimate how they're being assigned. Okay? So we start from trip generation. How many trips are being produced or attracted for each zone? Right? You can do the steps into trip distribution, you do mode split, and then you do trip assignment. And so you do these 4 steps, and at the end of the day, what you'll get is how many trips per link. So how many trips per section of route, for example. So this is what you're going to learn in week 2 to week 4. What I want to mention is that the scale is increasing with each step. So trip generation is very broad, from one zone to another zone. 2, to a really localized scale where you have let's say, for example, the parts flows for node for a part, let's say Windsor Road. You have 500 cars on Windsor Road per hour. That's what you're trying to do. So you've given what's more broad from let's say let's say I have this X number of trips within Sydney, right? You start from that's trip generation. So that's trip generation, and you do the steps. So for trip assignment, how many cars per section of road from, let's say, Old Northern Road from Castle Wood Balkans, for example. That's trip assignment. So what you do for a zone, right? You have this number of people, right? And let's look at it individually, okay? So trip generation in a nutshell is how many trips to and from each zone, okay? So to and from each zone. How many trips? So we have this zone. So how many trips are we doing to and from each zone? Trip distribution is specifically where are they going, okay? Where do I need to go? Mode choice. So that's trip generation number 1. Trip distribution number 2. Mode choice. Which mode am I going to take? Am I going to drive? Am I going to catch a bus? Am I going to catch a train? There's many different types of modes that exist. Am I going to cycle? Etc. And then you have trip assignments. So let's look at it simplistically. if we have 3 roads, say you have Old Northern Road, and then you have the Northern Road, and then you have Windsor Road. 3 different types of roads, right? Which road should I take such that it's in equilibrium? So we're going to focus on the concept of equilibrium pretty soon, but which road should I take and how many flows are in each part? So that's that in a nutshell. Trip generation, how many trips to and from each zone? You're going to learn that in week 2. So we need to determine trip demand. So how many trips to and from each zone? Am I recording right now? Yes, I am. Okay. So how many trips to and from each zone? So how many trips to? That's called attractions. Okay. And how many trips from each zone? That's called production. So if from one zone, let's say zone A, I need to produce trips. How many trips am I producing out of zone A? So that's production. Okay. And I got another zone B. How many people are going to B? So that's attracting me. Zone B is attracting X amount of trips. So just going to repeat that. Zone A. How many trips is from zone A? So that's production. I'm producing number of trips. And then you have zone B. How many trips to zone B, right? Say that zone B is a shopping centre, for example. Very simplified. How many people are going to the shopping centre, for example? Different types of models that we can use. We can use growth rate models, trip rate models, cross-classification models, and regression models. This is the growth rate models. So the number of trips, right, that's being produced or attracted, pardon me, is based off of this formula. So T equals to G times T. So the future number of trips, which is the one that we need to look at, is equals to the current number of trips times that by a growth factor. And that growth factor is usually given to you already. You also have trip rate models as well. So you have the number of trips is based by many different variables, okay? For example, in this case, labour force participation rate, not work at home rates, peak hour ratio, you can just, in this case, you can just multiply them. And you times that by, so those are the factors, right? Labour force participation rate, not work from home rate, peak hour ratio, and you multiply that by, let's say, population, the explanatory variable. So that's one type of model. 3 is a cross-classification model, category analysis model. So really, for example, we have trip rates, then production, times that by production, right? Okay, and so let's look at this example, right? Given daily trip rates, a trip per day for each household type. So people in the recording, right? So I should go to the laptop. I'm not sure if you can record and you can see it. Pen. But if you have a look at the left-hand side, right? Daily trip rates, trips per day for each household size. So they're giving you data, right? Why is it not? Oh, yes, here. They've given you data, right? So daily trip rates, trips per day for each household type, right? So for example, if I look here, you have 4 vehicles available per household, so you have 0, right? But you have 1 person per household. That's per trip, that's 0.57, right? That's a rate. You multiply that by the population, right? So in this case, 0.57 times that by 100 will give you 57. Okay, so that's future trips generated based from that thing. Okay, based from the trip cross classification model for that particular situation. So for that particular situation, 0 households, 0 vehicles per household, but with 1 person per household, that's 57, right? What you do from here, you just sum them all up and they'll get you the number of trips in each zone. In this case, it'll be 5,760.1 trips. You also have regression models as well. Give you a regression formula and then you can just use that. Okay? So that's week 2. That's trip generation. I feel like that should be straightforward. The more challenging bit is trip distribution. So where am I going? So you have these zones, right? So from trip generation, what we've found is that we've had the total number of trips generated by the zone. For example, we have had 5,760 trips. So trip distribution looks at where they're going. So for example, from zone 1, you have X amount of trips being generated. But from zone to zone 2, you have a number of trips being attracted. So how many trips specific, you may ask? So we're looking at for the left-hand side, which is production/attraction for each, right? So that's trip generation on the left-hand side, okay? And trip distribution is the right-hand side. So where are they going? So from what's the trip? How many trips is from zone 1 to zone 2, for example? And there's two different types of models: growth factor models, and gravity models. The more important one is gravity models. Growth factor model uses a uniform growth factor. So Vij is the number of trips from zone I to zone J, sorry. Again, Vij is the number of trips from zone I to zone J. So what you do is that you have this growth factor where Vp is the total trips predicted in the future and V0 is the total trips observed today. You find this growth factor, right? And you multiply all Vij by this growth factor. Okay, you can also have an average growth factor, so average of the production and the attraction growth factor, and you multiply that with J. And you also have many different other methods as well. But the more important one is the gravity model. So those who's watching on the recording, maybe in week 9, week 10, right? And those here right now, what you guys need to do is you need to remember this formula because that's not in your formula sheet. So the number of trips from zone I to zone J, right, is equals to the total productions from zone I, multiply that by the total attractions in zone J, times that by friction factor. This friction factor can be either given to you or you can formulate through this formula. Okay? So, in terms of this friction factor, say we're looking at travel time. When there's an increased travel time, right? Because in this case, there's an inverse relationship. When there's an increase in travel time, this friction factor decreases, and as a result, because number of trips is proportional to friction factor, if travel time increases, there in this example, what this means, friction factor decreases, and as a result, the number of trips from I to J would decrease. Okay? And often we need to, and this may sound a little bit gibberish right now because it's week 1 at the moment, but we need to look at the fully constrained model. Okay? So forecasted productions and attractions are matched upon completion of the distribution process. And this requires an iterative approach. Okay? So what's happening is that the total number of attractions being attracted to and from each zone is equal to the total number of productions. Okay? So it has to equal to each other. So what you do is that, it may sound a bit unknown right now in week 1, but you need to find what's observed. Okay, so this is what they give you. Okay, they give you your total number of productions and total number of attractions based on trip generation, which is the first step. And the second step is that what you need to do is then you need to use this model to determine Vij, and then from there you sum it up. That's what we estimated, okay, from the gravity model. That's the first step that you need to do. The second step you need to do is what you'll see is that you'll see that the total number of productions is not equal to the total number of attractions. They're not equal to each other. So what you need to do is you need to conduct row and column factoring, and then you need to repeat step 1 and step 2 until a given threshold is reached. For example, if the question says a 5% threshold, it has to be within this ratio. So I understand right now you may not understand what this means, right? But in the workshops in the next few weeks, there will be a few questions on this, and we'll work through this together to see how to do it. Okay? That's trip distribution in a nutshell. Modal choice is determining which mode should I take. Should I take the metro? Should I take the train? Should I take the bus? So how many travelers will choose each mode of transportation, right? And we do this given the number from zone A to zone B. You have, let's say, 5,000 people. What percentage of each would choose to take the train or take the car or take the light rail? We're looking at that, okay? So some of the factors that may influence that may include individual characteristics of decision makers, mode attributes. So in terms of mode attributes, there's two types of mode attributes, generic and mode specific. So generic can apply to every single mode, okay? It can, so for example, travel time, okay? However, mode specific is something that is specific for that particular mode. For example, how long do I have to wait for my bus? How long do I have to wait when I transfer from the bus to the metro? How long is the wait time? So those are some of the characteristics that we need to consider when we choose the different types of mode. Okay. Unfortunately, what DV will tell you is that transport generally has negative attributes. People hate traveling, hate getting stuck in traffic. They hate using public transport. Okay. So what we need to do is that we need to minimize these negative attributes. Okay. We're going to get introduced to the topic of utility, and the topic of utility will tell us how we're going to choose the mode. So what we have is that we have the concept of utility. Okay. The utility tells us the degree of satisfaction people derive out of their choices. So there's two ways of thinking about utility. We can maximize utility, but in a transport perspective, because transport usually has a negative utility, we need to minimize the disutility. So technically in transport, what you'll see is that when you have this utility function, which I'll introduce right now, if it's negative, we need to make sure that the negative number is not very big. Okay? So how do we calculate utility? Utility is calculated by this function. Okay? It's what they call a utility function. So there's a mathematical formulation that in an exam that they'll give you. So you have this modal bias parameter, which they'll give you, minus, let's say, for example, minus this, this coefficient, times that by the cost, plus that, times level of service, plus minus that. They would have given that to you in the exam, okay? But this is what transport planners do. They figure out what the factors are, and they, let's say, have a mathematical model to see what's the probability. And the first step to do that is through utility, okay? So we need to calculate what utility is. And what you'll get at the end is that you'll get a number, utility. And often in transport, that number is negative, okay? And we want to ensure that negative number is not very big. So I'd rather, you'd say, for example, you have train, utility of -1. However, car of utility of -3. Because a car has a utility of -3, which is lower than the train, which is -1, then the train is more favorable. Okay? So that's what utility is. So we have this concept of utility, okay? But how do we have this concept, we have this number of utility, but how do we translate this to the proportion of trips per, how do we translate this to the proportion of trips taken by each mode? What we do is that we use the multi-nominal logic model, which is this formula, which is a function of the utility. So you have all the utilities for you calculate the utilities for the different modes. For example, you calculate the utility for a train, calculate the utility for a bus, calculate the utility for driving, right? So the probability of user choosing the mode of I, right, is equals to e to the power of the utility of that mode in question. Divide that by the sum of e to the power of all the utilities, okay? If that makes sense, okay? So DV will go through how to do that, but say, for example, you want to find what the proportion of people traveling by car is, okay? So probability of the people traveling by car equals e to the power of the utility of the car. Divide that by the e to the power of utility of the car, plus the e to the power of the utility of the train, plus e to the power of the utility of the light rail, plus e to the power of the utility of the bus, except plus ... of all the modes out there. Okay? So now we have our trip distribution, and now we have our proportions for our different modes. So our car, our bus, and our rail. Okay? And we just multiply that by that like factor by that like that. Let's say 70% car, 20% bus, 10% train, based on that function. We can just split it to the two. And you also have independence of irrelevant alternatives as well, which is which is just a characteristic for each mode and their attractiveness. So sorry, just ignore what I said. Just reading off the notes without thinking, but yeah, this is just a property of utility, okay? So and the property of the MNL model, so the multinomial logit model. So the probability of, let's say, mode A, divide that by the probability of mode B is equal to the function of the sum of the difference of the utilities. That's just key thing to consider. They may ask you that question in the final exam or the midterms. The midterm quizzes. You also have that as well. I think Divya will go over that. But basically, if you have a red and blue bus, you need to combine them together because basically they're the same thing and the model's not 100% accurate. Tripped assignment is depending on the mode I choose, which route should I choose? Okay, so if I look at cars, for example, and there's 3 roads: Old Northern Road, the Northern Road, and Windsor Road. Okay, how many cars on Windsor Road? How many cars on Northern Road? How many cars on Old Northern Road? So which route do I choose? So what are the link flows on the network from an origin to a destination? If we look at cars in particular. So network equilibrium, okay, is important. And what that means is that travel times are equal on all used paths between an origin and a destination. There's many different solution methods that we can do. The main ones that we're going to look at in 73401 is algebraic and iterative framework. Let's look at the algebraic framework first. What you need to do is that there's 3 main formulations that you need to consider. 1, equilibrium conservation. Okay, this goes back to the idea of networking equilibrium. So travel times for all the paths are equal from an origin to a destination. For example, we have a network here from node 1 to node 2. And you have 3 different roads: link 1, link 2, link 3. Okay? The travel time from link 1 is equal to the travel time of link 2 equals to the travel time of link 3. Okay? So travel paths from node 1 to node 2, from travel time from zone 1 to zone 2, not between nodes, but between each zone, is equal. Okay? So you have an origin and you have a destination, right? And equilibrium between one origin and one destination is that all the travel times, right, for all the paths are equal, okay? And that could include multiple paths, okay? So you need to consider that. The second thing that we need to consider is demand conservation. To say that the total expected trips is equals to 5. In this example, if I'm looking at origin is number 1 and destination is number 2, what I'm looking at is that link with the flow in link 1 plus the flow in link 2 plus the flow in link 3 is equals to 5. That's for simple networks. And for more complex networks, we're going to look at is that all demand must depart from the source node and all demand must arrive at their destination node. So that's just another way of doing it if there's a more complicated example. Okay. Number 3, flow conservation. So no vehicles can be lost within the network. So any vehicle entering a node must exit the node. Okay. So in this case, x13 plus x23 equals to x34. Okay, so any vehicle entering a node must exit the node. So that's just a clear example here. So in this case, let's just ignore what the paradox says for the time being. But say this is a complex network. So we're looking at one node from origin is number 1, destination is number 4. The 3 different paths, there's many different paths we can take. You can take 1 to 2, then 2 to 4, 1 to 3, and then 3 to 4, 1 to 3, 3 to 2, and then 2 to 4. So the travel times between equilibrium says that travel time from 1 to 2 and 2 to 4 is equal to the travel time from 1 to 3 and 3 to 4 is equal to the travel time from 1 to 3, 3 to 2, and then 2 to 4. Okay? The travel time to 1 to 2 plus travel time to 2 to 4 equals the travel time of 1 to 3 plus travel time to 3 to 4 equals the travel time of 1 to 3 plus travel time to 3 to 2 plus travel times to 2 to 4. That's one example. And that's formula 1. Another formula is, say that we have 5 trips total. So what I can say here next is that 5 is equals to x 1 to 2 plus x to 1 to 3 plus, okay, ignore that rubber, okay. And that's also equals, so that's demand conservation. So all the demand must go through the origin and all the demand must arrive at the destination. So that's equals to x 2 to 4 plus x 3 to 4. That's 3 to 4. Okay? So you can see here very clearly, 5 is equals to that plus that in terms of flow, and that's equals to that plus that. Okay? And the third formulation is pretty simple. You need to find all the formulations to and from each node. So for an example would be x, if we look at node number 3, x 1 to 3 is equals to x 3 to 2 plus x 3 to 4. Okay? That's just an example. So again, this fulfills equilibrium conservation, demand conservation, flow conservation. Solve these equations simultaneously. They would give formulations of time with respect to flow. They'll give that to you. Solve them simultaneously, and then you'll get your answer. So that's your algebraic solution. And your lecturer would have went through this Grass's paradox. But I think you'll figure it out when you do the equation. Iterative framework is another way of doing it. Basically network analysis. So you need to calculate the path travel times. Once you've done that, find the shortest path, and then you adjust the path choices towards equilibrium. So what we need to do here is that we need to determine the minimum path tree. So how do I get to so we need to consider a network, and from the network we need to consider the origin and the destination. Okay, so in this case, if I want to get from node 1, right, to wherever, what's the quickest way of doing it? So the tips that I have is 1, start from the closest nodes from the origin, test possible paths and eliminate long paths to the node. You may need a lot of rubbing out, so I recommend you to do it in pencil and have an eraser. Right, so from here, from 1 to 6, the travel time is 6, but from 1 to 3, the travel time is 3, so have that down. But if I want to go here, I can go from 1 to here to here, 6 plus here to there, that's 12. However, I can go from here to there, that's 3, from there to there, that's set, and that adds to 7. So from here to there, that's a quicker way. So I just eliminate this path. But you have to check each node, see if you can do better. Make sure at the end of each node, there is one unique path to get from the origin to each node. There's no real textbook way of doing this. The best way to do this is through practice, okay? Practice is so important. There's no textbook way of actually teaching you. I think you'll learn best by actually doing it. And then from here, you assign and combine the demand. So usually in this case, to simplify it, you'll be given demand tables, which is constant. Okay? And there's also limitations to the iterative model, but they'll be discussed in a later course. But at the moment, we're just going to simplify it such that demand for each path is fixed. Week 4, we'll be looking at, so those are the 4 different types of transport planning. We can produce the trips, so how many trips are being produced from each zone, how many trips are being generated from each zone, that's production. And attraction is how many trips being attracted to each zone. And then from there, right, from specifically where are they traveling to? Are they traveling from zone A to zone B to zone C, whatever. The third step is, how am I going to get there? We looked at utility and we looked at the formula to figure out the modal the modal probability, like the modal proportion, right? So 70%, let's say, for example, 70% on cars, 20% on public transport, 10% running a bike. And then step number 4 is, which network should I take if I drive, for example? When we apply the 4-step model, okay, in transport planning, this is the different types of output, right? So what you can do is you can evaluate different network design scenarios using a range of metrics. So you can see that and you need to link that to what's the effect on the community as well. So you have these quantitative impacts, the numbers on the nodes and links and all that. What is the impact on the community in general? Rank design options. So maybe you should prefer from this, you need to rank design options, which one's better, which one's not. And 3, choose scenarios that is best for the community. You'll also be in week 4. You'll be looking at traffic flow theories. These are the different types of elements of traffic flow. So you have flow, you have headway, you have density, and you have spacing. So I'm going to release this these slides, my slides, to you after the workshop. So keep an eye on the CevSoc Facebook page for that. And if not, you just have to contact CevSoc for it. This is just a summary of some of the formulas that you would need to understand. I'm not going to go through why they exist, like the derivations, but just take them for granted. And you need to rote learn them because they're not in your formula sheet. What we're looking at for speed is we're looking at space mean speed. Keep that in mind. I'm still on the... No, not on laser point anymore. So we're looking at space mean speed. Space mean says there's 2 different types of speed that you would have been introduced in week 4. Time mean speed, which is the algebraic average of all the speeds, and you have space mean speed, which also accounts for spatial distribution. That's just equals to the total distance traveled by n vehicles on a road. Divide that by the total time taken by the same n vehicles. You can also use the harmonic mean of the speeds as well, which is given by that formula. And mathematically, what you'll find is that time mean speed will be greater than or equal to space mean speed. And they will be the same when all the vehicles travel at the same speed. You generally use space mean speed for average speed because it considers spatial distribution. You'll also be introduced to times distance flow diagrams as well, and what the relationship to with spacing and all that. So, for example, you have spacing as well as headway. If you have on the x-axis, you have time. The difference between the two, all right, here horizontally, that would be headway, and the spacing would be the y-axis vertically. I think that's that. Okay, yeah. When you fix one thing to the other. And you also will be exposed to this flow speed density relationship. Q equals K times space mean speed. So when there's increased speed, that means increased safe spacing, which means decreased density. When we use a formulation, it's called Green-Shield's model, which assumes a linear relationship between speed and density. You need to remember this because they're not going to give you this formula. But in a nutshell, what it is, it's that there's a linear negative relationship between speed and density. Okay, so just remember this graph, okay? X-axis density, y-axis speed, and just have a negative gradient line, negative linear line. Okay, and you have these different types of parameters. You have free flow speed. So free flow speed is the speed when there's no density, when there's no cars on the road. Jam density is this density, the number of cars per unit length, when density is at its maximum and there's no flow, so it's congested. This is a speed density relationship, and that is key to our Green-Shield's model. What we can do is that we can derive a speed/flow relationship. Knowing that Q equals K times V of S, we multiply this velocity on both sides, you'll get this formula. So what you'll get is that you'll get this parabola shape. So you need to remember this, okay? Where speed is on the y-axis, flow is on the x-axis, okay? What you have is that your free flow speed, you have your maximum capacity, which is right here, so this is your maximum flow, right? And then from here onwards, what's going to happen is that speed's going to reduce, and at the same time, your flow, your vehicles per hour, for example, is going to reduce. So in this case, your congestion will occur. So that's not good. And you also have your flow/density curves. What you'll have here is that it's a concave up parabola. So you just have to remember that. And you just multiply that by k on both sides to get that. But all that's going to be explained in the week 5 lecture. I won't be too worried about that now in week 1. This is just a summary of everything. And you also have different types of models as well. And lastly, there will be a question in week 5, which is the fundamental relationship between traffic flow elements. So what I want to mention here is that we can classify the level of service for a particular road from A to B to C to D to E to F, and according to that graph. What the key message here is that it's qualitative. So it's very subjective. So I had to talk to Dee about it. So what's going to happen is that you see here, these widths from A to B, B to C, C to D, D to E, they're not the same widths, okay? Because it's qualitative, okay? Okay, so it's really up to Ausroads to determine the widths. So you need to refer to the standards if you're really nerdy. But in a nutshell, and that's what it is, and that's that. So in a nutshell, it's just it's qualitative. So that's the first part. That's for transport planning. So for whoever's doing 3402, you can log off, sort of log off. But at the end, I'll be covering some general tips. What you'll focus in week 7 to 10 is just is your road design. So you have your kinematics. You just remember your Survat equations. I'm not here to derive them for you. V equals U plus AT. S equals U initial UT plus half AT squared. Final velocity V squared equals initial velocity squared plus 2AS. Car has many different types of forces. You have a propelling force by the engine, or if it's an electric car, the electric motor. We call this F tractive. However, when you propel a car, there's 3 resistive forces that you need to overcome. You need to overcome the grade resistance. So when you travel up a hill, you may need more power. And you need to combat drag as well, which is air resistance and rolling resistance. So those are the formulas that are given to that you need to remember. I don't think they're in the I'm not sure if they're in the formula sheet, so please refer to the formula sheet for that. But that is something that you need to consider. Okay? And you also need to focus on the power. So power equals work over time. And if you do some rearranging of the formula, what you'll get is that power equals force times velocity. And you make sure that you use the right unit. So in this case, velocity is in meters per second. Now, in week 7, you'll also be introduced to the standard, which is Ausroads Guides to Road Design, part 3. The reason why there's standards is that we need to follow Australian standards when designing roads, because we can't just have roads that have separate standards. So the Europeans have one standard, Australia has another standard. You see, the reason why standardization, ensuring that everyone's on the same page. Efficiency, so yeah, you also have efficiency, economic considerations, aesthetics, and driving quality. In terms of these standards, I'm not going to go in depth, so it's up to you guys. You need to have a look at how to use those standards yourself. It should be pretty self-explanatory to familiarize yourself with the content and all that. I'm just going to quickly speed run for the last 10 minutes, and then, yeah, I do have to go. But road design, what does that involve? The main thing is we're looking at design for horizontal alignment, vertical alignment, and cross sections. And you also need to consider active transport. But those 3 main things are key for those 3 main things are key for this course, really. So you have your horizontal alignment, which is your curves, your vertical alignment, which is your hills, these are some of the things for good road design. If you're different types of speeds, you'll be exposed to design speed, operating speed, and you also have these different types of speed as well. So speed effects of side distance, horizontal curve radii, pavement, super elevation, traffic lane widths. And you also, this is really important, sight distance. So when I drive a car, what is the distance that I can see from where I am to the obstacle? And we need to provide sufficient sight distance to enable drivers to perceive and react to any hazardous situation. So this is the formula, okay, based from your AG standards. It's this formula on the right. I think that will be given to you, and there's two components to that: reaction time, distance. So the distance, right? The sight distance, the distance where when I see the obstacle, how far am I going to travel before I see it and react and press the brake pedal? And you also have braking distance as well. So how long does the car stop? So you have that. And that's important when we design our horizontal and vertical curves. So horizontal curves involve, it's not just a circular curve. It involves transition curves as well. And then you have your circular curve and then you have your transition curve. You'll be exposed to that. But the main consideration is really, you know what SSD is. SSD is on the right. SSD is reaction time distance plus braking distance, right? On the right-hand side. We need to ensure that our sight distance, S, is greater than SSD, because the SSD, right, which is a stopping sight distance, right, is the SSD, your stopping sight distance, is the distance that is the minimum for the car to have before it hits the object, okay? So we need to ensure that our sight distance is greater than SSD. I'm going to calculate how we do SSD later. We need to do that first. Once you've done that, we need to look at super elevation, which is banked curves, to ensure that the curve is suitable enough such that the car doesn't slip. So that's how we do that. So in terms of sight distance is that, right? So what's the distance, right, from where I am right now to till I see the obstacle, right? And it's calculated by these formulas. In this case, for horizontal alignment, that. And then you need to consider vertical curves. You need to consider super elevations, so banked tracks. This is the minimum radius for, say, vehicle operation, right? But the main thing here is that you need to, so this is from the lecture notes, but the main thing here is that you need to have this E value, which is given to you right here, right? So you have to ensure that you find what E1 is, you round it to the nearest 0.5%, and then from here, you plug this in here, and then you have to ensure that F1 is less than or equal to F max, which is per table 7.5 of AGRD. These tables will be given to you in the formula sheet. And this is how to develop super elevations. So you have these different types of lengths. So you have this, I think that says S, I think super elevation. So you have your, I can't see from here, but if you look at the slides, you'll be able to see it well. It's easier if I see here. So you have your tangent runouts, as well as the super elevation runoff as well, before the curve, and then that's how you do it, okay? And there's these different types of formulas. I think they're in the formula sheet. And that's how you develop it. So you have your normal crown rights here, and then as you progress through, you have that. That's your super elevation. So you need to reach full super elevation. And you also have transition curves, and those are some of the properties of transition curves. And so that's horizontal alignment. So vertical alignment, there's two different types of vertical alignment. So when you drive up a hill, there's two different types of hills, right? That you may see. You may see a sag curve, which is, let's say, concave up, and then a crest curve, which you can say concave down. Those are some of the properties, right? What we need to understand, when we understand vertical curves, we need to have an arbitrary parabola. Y equals ax squared plus bx plus c. Okay? And what we need to do is to determine the parameters. Depending on the situation that you're given, you need to use your derivatives. So you derive them, and then from here, you plug your initial conditions, okay? So in an exam, you start off with this generalized form, and then you solve for the two derivatives to find A, B, and C. So in this case, when dy over dx, right, if that's right, if x and that's equals to 2ax plus b. When x is equals to 0, you have the gradient, and that's equals to g1 at x equals to 0. You can substitute that. You do that the same with acceleration as well. And you also need to know what k is. I'm a little bit running out of time, unfortunately, but you have your high-low points. These are some of your offset distances, right, from your curve to the tangent. So those are some of the properties that would have derived for you. Now, how do we design them, you may ask? The first thing you need to do is you need to ensure S, right? You need to assume one of the conditions, right? So say that, for example, S is less than L, right? You calculate what K is, right? And all these parameters are right here, and you can get some of them from the AGRD, right? From the table. And then from here, you substitute this K value here, times that by A. And A is the absolute grade change, so the difference of the two different grades. So you have grade 1 here, grade 2. What's the absolute difference? That's in absolute values. And then you multiply them together and you find what L is. See if S greater less than or equal to L less than L is fulfilled. If not, you have to use the other one. Okay. And in this case, S is equal to an SSD formula. Okay. And you also, that's for the crest curve. So that curve is this type of curve. So for the crest curve, you need to do that, and then you need to verify the appearance criteria as well. Sag curves, it's pretty much the same thing. So assume one of them, okay? So assume that S is less than L. You find K, you substitute K in here, verify that it's correct or not. If not, you have to use that, and then you just fulfill your appearance criteria as well. And then you also have to consider constructability as well. And there's also in reality, you need to combine horizontal and vertical alignment, and you need to do it well. So really need to consider that when you do it. With 10 cross sections, that's just a simple summary of what it is. I think a common exam question, right, would be something like this, right? You've done CVEN3401, right, which is the construction. It's very similar to what you've learned there, but you need to find out how much I need to cut, how much I need to dig. You do this through the either the trapezoidal volumes formula or the pyramidal volumes, usually trapezoidal, I think. And you do that for the whole length of the road. Figure out where to cut, figure out how much to cut, figure out how much to fill. You have net material equals total fill minus total cut minus compaction. Usually compaction is equals, like, say 15% times that by the total cut. And then you have your net material, right? Which is total fill minus total cut minus total compaction, okay? So I know it's a lot, but this is an incredibly simple summary of the content from week 1 to week 10. So it may be okay that right now you may be overwhelmed. You may seem that you're just talking some gibberish, and we only have an hour, and unfortunately I don't have the time. I have to teach another class from 4 o'clock onwards, so I'm a little bit over time. But some of the tips that I have is that during the term, please stay up to date to the lectures and workshop problems. They're your main source of your learning, especially for your transport planning component, as you have through your 3 middle quizzes. Do your practice material prior to your 3 middle quizzes. Stew back, catch up to your lectures and workshop material. Skim over the theory for the past 10 weeks, identify any gaps in knowledge and work on those. Familiarize yourself with the formula sheet, see which equations are not included, are included, and know how to apply these on given formulas. And do plenty of practice materials, midterms and past papers to prepare for the exams. Right before the exams, I will skim over the theory for the past 10 weeks to just have a final refresher. And at the end of the exam, it's so important that you do your working out to show the market that I know how to do this. I know DVR won't give you marks if you do the final answer, so you need to show your working out to show the marker that, hey, I know how to do this. Remember to state assumptions and don't stress too much in the exam. Again, you need to put the hard work in yourself. Again, it's your achievements and it's your work, not mine. So if you put the input, focus the time on refining the topics that struggle the most, you'll do well. Remember to work smarter. So if you do well, be proud of yourself. So yeah, have fun. Hope that's a good motivator to transport. Some Q&A. So I'm happy to stay behind for around 2 minutes. I need to teach another class from 4 p.m. But if you have any further questions, just feel free to drop into Square House 214 around, I know this says 4:30, but I'm running over time, so say 4:45 and then I can answer them. So yeah, have a great day and good luck and best of luck. Thank you very much.
Quick round of applause for Matt. Thank you for the time.